Welcome to Course 4, Module 4, Chapter 11, which focuses on digital twins and the Internet of Things in circular supply chain management. The central idea is that circular supply chains need more than efficient physical flows. They need reliable information about products, assets, inventory, and returns across the entire lifecycle. IoT technologies provide this information through connected sensors and platforms. Digital twins use the information to create dynamic virtual representations of products, processes, and supply chain networks. In this presentation, we will move from the broad conceptual foundation to practical case studies, technical architectures, simulation models, and global applications. The goal is to understand both the strong potential of these technologies and the important gaps that still prevent fully autonomous circular supply chain decisions. We begin with the introduction, where IoT and digital twins are positioned as key enablers of circular supply chain management. We then look at IoT case studies that show how real-time product health and usage monitoring works in practice. After that, we examine the challenge of using IoT data to predict end-of-life timing and trigger reverse logistics. The middle sections explain how supply chain digital twins detect bottlenecks and how technical papers describe real-time IoT integration. We then turn to simulation for circular business models, scenario-based reverse logistics under uncertainty, and global implementations in Europe, India, and Thailand. The presentation closes with the main conclusions and research gap. Use this roadmap to connect each section to the next. We will start the introduction with IoT and digital twins as enablers of circular supply chain management. It frames the core question: how live data and virtual replicas support circularity across product lifecycles. This slide shows the complementary relationship between IoT and digital twins. IoT establishes the data layer. It captures information about product condition, asset performance, logistics status, and environmental conditions. This is essential for circular supply chains because managers need visibility into products during use and after return. Digital twins activate this data by turning it into a dynamic model of the physical system. A twin can support simulation, scenario analysis, and operational decisions. The chapter notes that IoT has the clearest documented connection to circular supply chain management, especially through resource optimization, waste reduction, and reverse flow visibility. Digital twins are still more emerging, but they offer an important pathway towards sustainable, data-driven operations. That distinction is useful when interpreting the following cases. The process on this slide summarizes the information loop described throughout the chapter. First, product condition is captured by sensors or connected devices. Second, the IoT data stream transfers this information through digital platforms, often using cloud or edge systems. Third, the digital twin updates its virtual representation of the product, process, or network. Fourth, scenario analysis tests possible actions before they are implemented in the physical world. Finally, the organization can take a circular action, such as maintenance, reuse, refurbishment, remanufacturing, recycling, or route adjustment. The important point is that circular supply chains require feedback. Physical systems generate data, digital systems interpret it, and operational decisions aim to preserve value. This sequence is the practical backbone of the chapter. Literature already establishes several important points. IoT supports circular supply chain management by improving material control, resource efficiency, transparency, and visibility for reverse flows. Reviews also show that digital twins support lean management, logistics visibility, scenario analysis, and efficiency gains across planning, production, and delivery activities. Industry 4.0 technologies more broadly are linked to collaboration and sustainable business models. At the same time, the chapter highlights what remains underdeveloped. End-to-end circular twin implementations are still limited, and live IoT data is rarely connected to formal end-of-life prediction and reverse logistics optimization. This means the field has strong building blocks, but the integrated decision system is still emerging. This balance between progress and gaps should guide the discussion today. Now we are shifting from concepts to IoT case studies. The focus is real-time product health and usage monitoring, showing how connected sensors support maintenance, service models, and lifecycle extension. Industrial IoT case studies show how installed assets can become monitored systems. In production machinery, IoT solutions collect detailed operational information, including processing times, setup times, alerts, performance metrics, and bills of materials. This information is transferred to centralized cloud systems, giving original equipment manufacturers and customers a remote view of production line performance. Other studies describe OEMs that use IoT platforms with high sampling rates and real-time availability to monitor the condition of fielded equipment. The practical value is condition-based maintenance. Instead of waiting for breakdowns or relying only on fixed schedules, companies can intervene when the data indicates a need. This reduces downtime, improves performance, and can extend product lifetimes. This helps translate raw data into service value. The evidence base is broader than machinery alone. The Mirage Smart Bicycle prototype uses encoders and hall sensors to measure steering angles and parts movement. That data synchronizes with a digital twin, supporting real-time monitoring, predictive maintenance, and design improvement. A circular LED lighting case shows how IoT infrastructure supports performance-based service models by tracking installed parts, system performance, remaining lifetime, and residual value. In pharmaceutical cold chain logistics, connected temperature and humidity monitoring enables quality assurance during storage and transport. Across these examples, the common pattern is clear. Real-time data is most powerful when it supports lifecycle decisions, including maintenance, redesign, service delivery, and reduction of waste or product quality loss. Each example links sensing directly to circular operational benefits. This slide expands the monitoring logic into a circular value cycle. The first step is observation. Sensors capture usage, condition, and performance data. The second step is prediction. Companies estimate failure, remaining lifetime, or maintenance needs. The third step is intervention. Organizations repair, replace, refurbish, or adjust operations before value is lost. The final step is redesign. Field data is fed back into engineering and business model decisions, improving durability and service offerings. The LED lighting case is especially relevant because IoT data supports maintenance, residual value estimation, and product improvement. In circular supply chains, monitoring is therefore not just a technical activity. It helps keep products useful for longer and improves future circular strategies. This cycle explains the strategic value of monitoring. Now we are addressing a key gap. Live IoT data rarely triggers formal reverse logistics decisions. Current research links sensing and optimization only partially, especially for product-level end-of-life timing. The missing link is an autonomous end-of-life trigger. On one side, reverse logistics models are well developed. They can optimize facility locations, collection networks, recovery flows, costs, compliance, and profit objectives. However, many of these models assume that returns are already known or estimated through static projections. On the other side, IoT frameworks describe how products can be monitored in use and how predictive data could support circular decisions. Yet these frameworks often remain conceptual and are not fully connected to formal optimization models. The chapter concludes that no mature, fully specified model currently ingests live sensor data, predicts product-level end-of-life timing, and automatically selects or optimizes the next reverse logistics action. Understanding this split clarifies why integration remains difficult. The current research landscape can be understood through three strands. The first strand consists of established operations research models for reverse logistics. These include mixed integer programming, nonlinear models, genetic algorithms, system dynamics, and simulation approaches. They provide network design capability, but usually without live IoT inputs. The second strand consists of empirical and conceptual IoT work. This research shows that connected products can estimate condition, remaining lifetime, and return-related uncertainty. The third strand is a research agenda for reverse logistics 4.0. It calls for data-driven, proactive planning using artificial intelligence, real-time data, and advanced optimization. The opportunity is to combine these three strands into a single integrated decision architecture. The chapter treats this combination as the next research frontier. This slide illustrates what an integrated model would need to do. It would begin with live sensor data from products or assets in use. The system would then predict the likely end-of-life timing for each product, not only general failure risk. It would also estimate the certainty of product quality, meaning the expected condition of a returned item and its suitability for reuse, refurbishment, remanufacturing, or recycling. Based on those predictions, the model would select recovery options and optimize reverse logistics, including collection, routing, facility use, and timing. The chapter shows that pieces of this logic already exist, but they are not yet combined into a mature autonomous system. This chain would make circular recovery more timely and precise operationally. This section will explain how supply chain digital twins detect bottlenecks. Simulation-centric twins mirror flows, capacity, and inventory so decision makers can identify congestion and test improvements virtually. Digital twins expose bottlenecks by creating a high-fidelity mirror of the physical supply chain. Formal models describe how materials, inventory, production capacity, and demand interact across stages. Real-time data keeps the model synchronized with current operating conditions. Scenario analysis then allows managers to test disruptions such as demand surges, longer lead times, stock variability, or transport delays. Optimization methods can search for better capacity allocation, inventory placement, or routing decisions. The chapter highlights examples in perishable supply chains, master planning under disruptions, and inventory management. In each case, the value of the twin is not simply visibility. It is the ability to diagnose constraints and test corrective actions before changing the physical system. This is why twins support both diagnosis and response. The chapter identifies 4 pillars that support bottleneck-oriented supply chain twins. The first pillar is dynamic modeling, including state space equations or discrete event simulation that captures multi-echelon flows. The second pillar is live data, because the twin must be continuously synchronized with sensors and operational systems. The third pillar is integration with machine learning and optimization, which helps identify performance drivers and search for better configurations under stress. The fourth pillar is structured scope. Frameworks such as the 7-element digital twin model and score-based approaches help define whether the twin represents a product, process, organization, supply chain, or network of networks. Together, these pillars turn a simulation into a diagnostic decision system. Together, they create the basis for actionable visibility across networks. Different bottleneck problems require different modeling patterns. State space twins are useful in perishable supply chains because they can represent relationships among production, inventory, and sales, while updating parameters with real-time information. Hybrid simulation and machine learning are used in master planning under disruption, where simulation captures complex interactions and machine learning identifies the drivers of performance. Geographic information system approaches can support global multi-echelon inventory and service optimization across locations. Logistics and warehouse twins focus on distribution assets and internal movements, where congestion and poor visibility often occur. Across these patterns, the common purpose is to reveal where physical flows are constrained and to test improvements before implementation. The choice of method should match the operational bottleneck being examined carefully. The following section focuses on technical architectures that connect digital twins with real-time IoT data. These systems move supply chains from reactive tracking towards synchronized cyber-physical management. This architecture begins with physical resources, such as shipments, equipment, warehouses, products, and handling systems. The IoT or Internet of Everything layer collects data through temperature sensors, humidity sensors, Bluetooth low-energy beacons, traceability devices, and other connected systems. Edge and cloud computing then support streaming, processing, storage, and integration of these data flows. The digital twin uses the processed information to create a real-time representation of the supply chain. In the most advanced examples, this enables monitoring, anomaly detection, simulation, and decision support. The key message is that digital twin value depends on technical integration. Without reliable sensor streams and computing capacity, the twin cannot remain synchronized with the physical chain. Each layer must work reliably for the twin to function. The chapter highlights several technical settings where integration is especially explicit. Pharmaceutical cold chain logistics is one of the strongest examples, because temperature and humidity conditions must be monitored continuously to protect product quality. An Internet of Everything layer streams data from sensors and beacons into a digital twin, enabling anomaly detection and real-time decision support. Digital twin-driven smart supply chains provide a broader enterprise view, where the twin mirrors physical operations and supports optimization and collaboration. Smart ports show how sensor-rich logistics infrastructure can feed near real-time simulations of material handling and shipments. Food supply chain research also emphasizes dynamic digital replicas that combine IoT, cloud computing, big data, artificial intelligence, blockchain, and supplier portals. These examples define the current state of practice. Real-time synchronization is demanding. On the enabling side, supply chains need distributed sensors, traceability devices, cloud and edge infrastructure, big data analytics, machine learning capability, and integration across portals and operation systems. These elements allow data to move from physical assets into a digital twin quickly enough to support decisions. On the barrier side, the chapter notes that this requires substantial bandwidth, massive processing capacity, and careful mapping between remote sensor data and centralized models. Another risk is that organizations may already collect tracking data, but the data remains disconnected from cognitive twin models. In that case, visibility improves, but full simulation and decision intelligence remain limited. Therefore, implementation is as much an infrastructure challenge as a modeling challenge for organizations. In this section we examine digital twin simulation for circular business models and material flows. The main idea is virtual stress testing. Testing circular operations before implementing costly physical changes. The WE disassembly example is one of the most direct circular economy applications. In this case, researchers integrated digital twins, virtual reality, and discrete event simulation to test configurations of an electronics disassembly plant. The twin replicates plant behavior and allows managers to simulate different layouts and process settings in a risk-free virtual environment. This supports circular economy goals because better disassembly procedures can improve material recovery and operational efficiency. The same logic also applies to food and logistics systems, where digital twins can test layout changes, demand patterns, facility locations, and inventory policies. The broader lesson is that simulation helps organizations identify wasteful designs before those designs are implemented in the physical system. This makes the case especially relevant for circular economy practice. The chapter makes an important distinction between operational simulation and full circular ecosystem simulation. Current research is strongest at the operational level. It can test plant layouts, warehouse configurations, logistics designs, disruption responses, and localized recovery processes. These applications are useful because they can reduce waste, improve material recovery, and support better resource use. However, complete simulation of circular business models and closed material loops is still underdeveloped. Conceptual work on digital twins for the circular economy identifies stakeholders, information requirements, and lifecycle roles, but calls for more practical implementation and performance testing. The opportunity is to extend isolated digital twin applications into synchronized models that cover products, materials, partners, and circular value creation. That limitation defines an important future research direction. This section will explain scenario-based reverse logistics design under uncertainty. Because live end-of-life prediction is not mature, planners use scenarios to test returns, product quality, and recovery yields. Reverse logistics faces several types of uncertainty. Products may return in different quantities and at different times. Their quality may vary, which affects whether they can be reused, refurbished, remanufactured, or recycled. Material recovery yields and conversion fractions are also uncertain, especially in complex waste streams such as electronics or batteries. Costs, demand, capacity, and environmental constraints can change as well. The chapter describes models for multi-product reverse logistics, sustainable network design, and electric vehicle batteries. These studies use scenarios, Monte Carlo simulation, sensitivity analysis, or system dynamics to understand how different conditions affect performance. The planning goal is robustness across plausible futures, not optimization for one perfect forecast. These uncertainties make robust planning more valuable than simple forecasting. The virtual experiment process usually begins with scenario generation. Researchers create possible combinations of demand, return quantities, product quality, recovery yields, costs, capacities, or risks. An optimization model then evaluates network decisions, such as facility locations, capacities, flows, collection strategies, and recovery allocations. Simulation experiments test how the network performs under uncertainty, while sensitivity analysis shows which parameters matter most. The outputs help planners balance profit, environmental impact, reliability, and service performance. This scenario-based approach is a practical response to uncertainty in reverse logistics. However, the chapter also suggests that future models could become more dynamic if scenario planning were combined with real-time IoT data and digital twin feedback. This process converts uncertainty into structured, testable planning assumptions for managers. Europe, India, and Thailand illustrate how IoT and digital twins support recovery, pharmaceutical cold chains, and agri-food waste reduction. The European case focuses on waste electrical and electronic equipment. Circular economy mandates and extended producer responsibility create pressure to improve reverse logistics and material recovery. Digital twins and simulation can help by creating virtual test beds for disassembly plants, allowing operators to test layouts and process settings before physical changes are made. The Indian case focuses on pharmaceutical cold chains. Continuous IoT data from environmental sensors and beacons can feed digital twins that monitor temperature, humidity, anomalies, and product quality risks. The Thailand case focuses on agri-food logistics. Digital twins can simulate warehouse layouts, seasonal demand, inventory policies, and transport flows to reduce spoilage and resource loss. Each case uses digital visibility to support circular or sustainable outcomes. Together, they demonstrate regional adaptation. Though the regional contexts differ, the implementation pattern is similar. Each case begins with a localized challenge. Europe faces variable returns and the need for efficient material recovery. India faces temperature-sensitive pharmaceutical distribution across complex routes. Thailand faces perishable agri-food flows where delays create waste. Each case then applies a digital capability. Europe uses virtual disassembly testbeds, India uses sensor-fed cold chain twins, and Thailand uses scenario-based warehouse and logistics twins. Finally, each case connects to a circular outcome, such as higher recovery yield, reduced spoilage, or lower resource loss. These deployments are not yet fully autonomous circular systems, but they operationalize sensing, simulation, and robust planning in real environments. This comparison highlights the transferable logic across sectors and regions. IoT and digital twins are most valuable when they are connected to circular supply chain decisions. IoT provides real-time visibility into product condition, location, and usage, which reduces uncertainty across the lifecycle. Digital twins then translate that data into scenarios, helping managers test bottlenecks, reverse flows, and recovery options before acting. The case examples show that the same logic applies in different regions. Better sensing and simulation can reduce delays, spoilage, waste, and resource loss. However, the key challenge is integration. Future circular supply chains need shared data, interoperable systems, and optimization models that can trigger repair, reuse, recycling, and logistics decisions automatically. In other words, technology creates value only when it changes operational decisions. Thank you for your attention. Next, we continue with Module 4, Chapter 12.